Hi, good to get connected again on the topic of welding. As you see here, we have discussed many other aspects of welding and some aspects of the defects in welding. But today we are going to deal little more into the defects and what could be our approach to first detect these defects and then how to overcome these defects in the easy steps. The left hand top photograph is the type of defects which we normally discuss, so I am not going to dwell more upon that. However, we will touch upon it. There are mainly three types of defects which we see it. The defects which originate because of the setup. If the setups are not done to its perfection, we are seeing that root gap, root face, included angle, mismatch, and so many other possibilities by which you can see there could be a defect because of the imperfection in the setup. And these defects or the remedial action is probably we know it, either we break the setup and try to correct it, but if that is not possible, then if we have anticipated earlier, we can give some taper to minimize the mismatch, or we try to do some waging and we try to do excessive fixturing so that whatever mismatch or other setup defects, they will not aggravate it further, as there will be a welding shrinkage or welding distortions. But there is a limit, and finally we need to accept it or we need to correct it post welding by once again either depositing extra layers so that there is a smooth transition between one end of or the one side of the weld to the other side. And these are finally not a very good practice, and designers will have always a suspicion on how these products will perform, because they have taken care while designing that the mismatch and other setup defects will be to the minimum or zero. So that's the first one. The second defects is where we can see it by the naked eyes. Like the first one, the underfilled, we can see that welding has not been done fully into the groove if that is required to be filled up. Obvious, this one remedy is that we need to add more runs and ensure that the weld groove or the fillet or the overlay or buttering or the other applications of welding which are used are completely done to what is required as per the standard code or the design. The second defect is undercut, which is also a surface defect, and this welder will find it, only experienced welder will find it while he is welding it through his screen, but otherwise for a new welder he may miss out, especially the small fine undercuts which emerge on cooling. After cooling in the heated condition, you feel as if you have done a good weld, but when it cools down, you see that there is a undercut, sharp undercut sometimes, which can be a stress riser. So if you happen to see these undercuts after the welding, you need to immediately little bit clean, grind, make extra space for you to weld and deposit additional runs to cover it up properly. Same is the third one, the pore penetration. Like the underfill on the top side of the welding, there could be a pore penetration on the bottom of the weld, the other side of the weld. But for this you need to have access towards the other side and see it with your naked eyes. If you don't have access, like in tubes, pipes, or some of the big shells where you cannot go inside, then the penetration welder through his screen is able to judge that whether the keyhole what he creates while welding the root run, is that getting fully filled or penetrated Indirectly we can see it based on the depth of the welding and the amount of filler wire he has consumed, and that could be another good indicator whether we have achieved a full penetration, or else for these inaccessible things you may have to use a boroscope or some mirrors, or you may have to take x-ray, ultrasound, then only you will be able to see this poor penetration. The fourth defect, or the right hand top lack of fusion, is a defect where sometimes it is difficult to miss out with the naked eyes, because you see as if it is penetrated fully, so you assume that while it has penetrated, it has also fused on the side walls or the edge preparation which has been done onto the two plates or the two jobs which are getting joined. But actually it has penetrated, it has only come out of the groove, but it has not fused on the sides. Now surely if that happens, visually it is difficult to see it. The dye penetration test sometimes will reveal in case the root is penetrated and not everywhere it has fused. So visually you will not be able to see that, but the red dye will surely come out as you put the developer on the other side. The fifth one, the spatter. Obviously these are on the surface. Visually you can see it. While welding also, through the screen you can see the sparks which are getting generated and the droplets of weld getting deposited onto the side of the weld on our jobs which are getting welded. And then this also becomes activity to clean. These could be sometimes big ones which may have a good fusion, so you have to grind and remove it, and these are not good aesthetically, as well as in sensitive alloys like alloy steels. These could be a stress risers in case they happen to be the big ones. Porosity most of the time is internal, very rarely, or sometimes you can see it on the surface also open to naked eye and you can correct it. But surely an experienced welder can see the gas which is bubbling into the weld pool, and if it is having a very aggressive action there, then porosity is surely going to come. And good welders I have seen, they are able to get them improved while they are welding only. Either they will stop immediately, do whatever correction required, either in the gas or in the shielding or in the angle of your torch or electrode or your other cleanliness issues if they are there for the porosity, and they will surely able to improvise it. But otherwise you will have to wait for X-ray to happen or a dye penetrant for a fine porosity which is exposed to the surface. The next two defects overlap once again by measuring the width of the groove and then later on finding it out what is the width of your weld, and then by using some very fine wires you can try to insert between the overlap region of the weld and the base metal, whether this overlap, is it good or is it only on the surface. That means the excessive current has melted material more in the last layer because you are in a hurry to finish and go. So, but it has not actually burnt the parent metal which is required. The parent metal has to also melt to have proper bond or a fusion. If that doesn't happen, overlap is not good. Otherwise, having 1.2 millimeter overlap on each side is a desired welding practice, and one should have it. Inclusions, slag inclusions or other foreign particle inclusions, those are once again stress risers. It is a imperfection in the weld. It is not the weld metal which is actually conducting or having uniformity in the weld metal, and that's where it is called as a defect, and those are not acceptable. Those are required to be removed. Sometimes they are very brittle, sometimes if it is a slag it will be having no strength, and the cross-sectional area of the weld will substantially come down because of these inclusions, and you will not get the strength which is desired. The next defect, the last row, excess reinforcement. Now, any reinforcement which is a smooth transition, like a good speed breaker, if we are able to go over it, you hardly feel any jerk or a jump. But if the speed breaker is very tall, very narrow, very sharp, you will see whatever speed, even if you are going to go at very less speed of 1-2 kilometers per hour, still you will feel a jerk. Even if your car is the high-end car like Mercedes, Toyota and all, it will still have it because the nature of the speed breaker, and exactly that's what happens. And you can see from the figure itself, and this is what the reality also many times we see. The welders who are not able to see the profile of the weld through their screen, they'll end up into, or the parameters are bad and they're using the excessive arc length. This is what will happen. It will spread, it will have only in the center portion lot of deposition, but the rest of the area is getting melted and flown, and that's where the width goes up. So reduce your arc length, reduce your arc voltage, use proper current. I'm not saying that use low current or a medium current. Even if it is within the range, you should be able to do it. Or if you want really a wider width, you should weave it and have a dwell. The dwelling in weaving is very essential. Dwelling is you wait, stop at both the ends of the width which you are covering, and then deposit, allow that dwell, that is the wait period, to deposit more material there and improve the profile. Smooth transition is not a stress riser and it is good. Code recommends 1:3 taper for any smooth transition in dissimilar thicknesses, or wherever you have transitions in the nozzle or in our other areas, in the pipelines or in the structural members. Cracks, obviously, because of improper shrinkage, improper parameters, improper welding consumables, you will land up into the metallurgical defects. The cracks, when the material is cooling down, it doesn't cool uniformly, and there are certain voids which create like a porosity, but porosity is a small defect, whereas here it is a large defect which actually creates a planar defect. It is not a volume defect, it is a planar defect, a crack, and those are very, very difficult to take up under the load. Cross-sectional area in that particular plane drastically reduces, and the weld cracks or the entire equipment has a failure. The last defect, that is the burn through, is mainly because of the defect which occurs when you use excessive current, larger gap, lower thicknesses, and improper welding speeds. So there are many reasons for burn through, and if you are not having a good control over your welding, the burn throughs are unavoidable. And once you have a burn through, you really make a larger root gap in that area, and then to fill it up is a real trick. So you should not try to bridge this gap, the burn through gap, in one go. Rather use a buttering technique after, of course, grinding and re-preparing your edges to smooth transition. Bring slowly material by depositing on both the edges to a desirable root gap, and then use proper current to fuse it again and join them together. If you try to join them together in a larger gap after a burn through, the weld metal will be very thin, and that thin material, while it is shrinking or while it is cooling down, the shrinkage cracks, it will not be able to sustain and it will crack. And this is what happens if you happen to make a concave welding in a root run. If you try to give a concave welding, then the thickness at the center of the weld becomes very less. It cannot sustain, and it fails or breaks and looks like a burn through or a crack in the root run or in the penetration. And these are all the defects which only by improving parameters and adjusting your angle of the torch or of the electrode you can improvise it. So these are the standard defects which we have seen, but as we have been discussing, that welder's job is not only to make a good sound weld, he has to also ensure that finally the equipment passes the dimensional requirements, it passes all the design code standards requirements, and there should not be any distortion, whether it is angular as it is shown here, which is a very common defect what we see it in the long sims. Bowing, which is also another common defect, the diameter at the two ends of the shell you will see suddenly going up, and the diameter in the center of the weld or the center of the shell is less. The longitudinal shrinkage or the transverse shrinkage, these are all the defects which by using a proper technique, proper fixturing, proper sequencing against the neutral axis, or even sometimes changing the position of the weld and having two operators in 3G position simultaneously welding on each side of the weld, or by heating or cooling or preheating, post heating. These are all the different techniques by which you can do it, and it doesn't happen only in the butt joints, but you can see here it happens in the fillets also, and how bad the fillets will turn. Both, I mean, the vertical rib as well as the base on which you are actually trying to weld rib, both may have distortions, and that is not acceptable at all. So certain means of the using a long simmer or pre-cambers as it is shown here, or using a proper sequencing or stiffening the joints, these are all the techniques which are used. But along with the internal defects, these are all the external, the third kind of a defects, which is the operation successful, patient died, you have a good sound weld meeting all the NDT parameters, meeting all the strength requirements, meeting all the visual requirements, but it is having a distortion by which the equipment cannot sustain the design loads and the equipment is going to fail. So we have to really take care of both these kinds of defects, and those defects will only ensure that we will be able to make a good equipment. And there are other remedial things which we will be able to take it up. Now let's go little more and understand what happens beyond this weld. What we have seen in this slide is what we have seen in the earlier slides is the typical defects what we see in internal in the weld, but we have not studied what happens to the heat affected zone, because welding engineer's responsibility, as we discussed, has an important role to play, that when you are welding, not only you are taking care of your weld as it is shown here, the parent metal is already taken care, we have taken the graded material, tested material, so this side is not really a worry for a welding engineer, because that's the job of the planners, the procurement agencies, the QC to give us the right material for doing the equipment and joining it. We select a good consumable, so welding engineers, the first job is taken care, he selects right parameters by which we will be able to weld it properly. But this intermediate zone, which is undergoing various heat treatments as it is shown from this iron carbon diagram and from this chart, that at the time of at the center of the weld you have the melting point plus a little higher temperature, 30, 40, 50 degrees superheat for good flowability of that material and ensuring fusion, penetration and other parameters which are required. But at the same time, since it is a metallic material, it has a conduction coefficient of expansion and other associated properties of a particular material, and if we are not able to take care of those properties and manage our heat, manage our cooling, manage our fixturing to ensure that not only we protect parent metal, we not only protect the weld and get a good weld here, a very thin, maybe from few microns to 2, 3, 4, 5 millimeters depending upon the thickness and the type of material and the material properties, like some materials have a good coefficient of expansion, so they will expand, contract to a larger extent. There are some materials which have very low coefficient of expansion. Similarly, thermal conductivity, a good thermal conductivity like aluminum, copper will flow the heat and make the entire surface hot. Like stainless steel and others, those who have a poor conductivity, they will try to accumulate the heat. The mild steel, which is absolutely good in all aspects of these physical parameters, is always good to have a weld on a mild steel. But you don't have mild steel giving you the strength, the corrosion properties, and high temperature, low temperature properties. So you select various other alloys, materials by which you need to really take care of this heat affected zone. And the heat affected zone, as you see here in this, the strength and the ductility comes down drastically different in the heat affected zone because of these various heat treatments which this heat affected zone is going to undergo, from the melting point to room temperature, and each of these zone will give different grain size, different grain orientation, and this makes the properties to vary even though the chemical composition is not going to change. And as we go to high strength alloys, you will see sometimes the strength reduction, especially see this point which is below the point of the parent material, and that becomes a real challenge because the strength is reducing, ductility goes up, but in the heat affected zone near to the weld, the ductility comes down even though the strength is going up. So this region is becoming very brittle, this region is becoming very ductile with very low UTS, so it will start yielding faster. And the same thing happens in the mild steel also to a certain extent. This zone which happens in the quenched and temper steel doesn't happen in mild steel, and the strength doesn't come below the strength of the parent metal, but variation is surely there. The high strength or the hardness and the low ductility happens in the mild steel also, and this happens in every alloy, whether it is nickel, copper, titanium, aluminum, and other cobalt based alloys. Heat affected zone is unavoidable and we need to take care of it. So in summary, for this particular topic, I am saying that that defects are internal, defects are within weld, defects are external to the weld, visual defects are there, NDT detected defects are there which are hidden, which are inside the weld. The defects which are coming because of poor setup, defects which are coming up because of the poor fixturing, or not using a neutral axis or balancing the weld, or not using a proper technique like step back technique, we will end up into distortion or deformation or some mismatch, shrinkage. So all such defects are to be taken care while welding, and our different videos are trying to get us into different aspects of our welding, but those are required to be taken care. And I'm sure, like the other videos, you like this video on the defects. It's a very quick 20-25 minutes video, but will give you a good understanding of various defects, and more than defects, the overall weld efficiency, weld joint efficiency, how are we going to do it, the distortion, shrinkage, other defects in the welding are also not acceptable, and that's the responsibility of a welding engineer or a planner to really look into. So thank you very much for this particular small video, and hope to get your comments on it. Thank you.